Okay. So 3.3, we're going to talk about what's called Taylor polynomials. So this is about approximation. So yesterday I mentioned at the end of class, or quickly drew up on the board, a random graph and had the line and how you could approximate some point close to it. And I mentioned you've done similar things to that, but what we're going to do, we're going to expand upon that and kind of approximate it using curves, so the curve will get closer and closer to what we're trying to approximate. So it says polynomial functions can be used to approximate other elementary functions such as sine x, e to the x, and natural log of x. So we're going to go ahead and just jump right into an example and get started. So example 1. Find the equation of the tangent line for f of x equals sine x at x equals 0. Then use it to approximate sine of point 2. Is this an over or an under approximation of sine of point 2? Alright, so we want a tangent line. So first thing we need to do, let's list out, we know f of x is sine x. Okay. And if we are, they're talking about x equals 0. So if we were to plug in 0, f of 0 would be what? What would f of 0 be? Okay, it would be 0. Okay. If we take the derivative of sine, hold on a moment. Hello? Yes. I can. Alright, bye. Caitlin? Office? Do you know, are you leaving or will you be back? You're not sure? They just said. Alright, just head up there. If you're leaving, you come back and get your stuff. But okay, so the derivative of sine is?
Cosine.
Yeah, cosine. It is cosine. Cosine x. If we were to evaluate at 0, it is 1. Okay. So we have a point and we have a slope. So what is our equation if we have the point and have the slope? It's going to be y minus what? Which is, we have a point and have a slope. We just figured them out. 0, yeah. Y minus 0 equals, the slope is 1, then x minus 0. So we get y equal to x. And as we go on, you're going to understand these a little bit more, but this is known as a first degree Taylor polynomial. First degree Taylor polynomial. So this is what we're using as the approximation. So we're saying y is equal to x. Okay, we want to approximate at what value? What value do we want to approximate at? 0.2. So using our approximation, we're saying that y is about 0.2. That's our approximation. Since we have the ability of using calculators and more broad technology than they would have back in the day trying to solve this, this is why they used the approximation, how would we have actually found what the value is at 0.2? What would we do with it? If you have your calculator, you can do what with the 0.2? We want to know the actual. Exactly. We can evaluate sine of 0.2. So go ahead and grab a calculator if you don't have it already. Sine of 0.2. 0.199. Okay, that's your actual. Very good. So can we see that the approximation was pretty close to the actual? Okay, now remember that was using the first degree, so first degree polynomial, Taylor polynomial, would be just a line, so we're using that line to approximate it. The approximation was close at 0.2, but it was a little bit off. Not far though. So, was it an over or under approximation? Over approximation. Not by much, but a little bit. Any questions so far? All right. The equation of the tangent line used in example 1 is called the first degree Taylor polynomial, and we already labeled that up above. Taylor polynomials of higher degree can be used to obtain increasingly better approximations of non-polynomial functions within a certain radius from a center of approximation x equals c. So they're calling this center of approximation that we'll use at x equals c, and we're going to use that more once we get through more examples. So on your calculator, graph in y1 equals sine x and use the following window. And then in y2, graph successfully, adding an extra term each time, this one. So what we're going to do first, go to y1. And put in sine of x for the first one. The window, we want to go from -9 to 9, and then -4 to 4. So this is just with y1 graphed. You should get something like this. Let me know when you've made it this far. Eric, we're at least this far? Good. Madison? Not letting you graph? Okay, so that's graphing the first one. So this is the function we're talking about. We're talking about sine x. This is what the sine x graph looks like. We had, in the example 1, approximated it at 0.2, so like very close to 0 here. We approximated it, and we used that y equals x to help us approximate it. All right, so now it says in y2, we're going to do multiple things. First, we're just going to enter x, which is what we did up above, and we're going to look at it. Then we're going to add the second term and look at it again, add the third, add the fourth, and continue to see what it looks like. So in y2, just put x, and then graph it. Do you see how for a little ways starting, the center for this one is considered at 0 there? That's where the sine function's starting at 0, 0. That's our center. And our line, our approximation, goes right through there. And do you see how for a while it looks like it's a pretty good approximation? Until the sine function starts coming back down, then our line goes off. But for the first few values of x, wouldn't the line be an okay approximation? And didn't we show that up above? Yeah, so now let's go back down to where the x is, and let's add the next term. The next term is the x cubed divided by 3 factorial. You should get some kind of graph that looks like this. Have we made it this far? Not yet, Eric? Okay. So again, this is on your y equals 2. You have the first two terms entered. The x and the minus x cubed over 3 factorial. So that we only have those two terms entered so far. And if we look at this graph, we no longer have the line. We still have the sine function. We haven't changed that. But now we have this graph here. It goes like this. What do we notice about this one compared to the line? Yeah, a little bit further, we can approximate this curve of sine a little bit better. We can see that it starts deviating right here and it goes off, but a little better than the line did when the line started going straight up. Alright, let's go back to the second one again and let's add the third term. So now this would be plus x to the 5th divided by 5 factorial. Once you graph this one, what do we notice about when we have 3 terms? It's getting even closer. From the center here we see it goes all the way up, wraps around, it goes back down, and then it starts to deviate off. So we could approximate this one a little further. The line would have been way up here, so the line would have been way off in the approximation. But this one's getting closer and closer to our original sine function. Alright, let's go ahead and add the minus x to the 7th then. Alright, so as we've gone through this process, what have we noticed, and what do you think will happen if we continue? Okay, with each term we get a better and better approximation. It goes a little bit further each time. Now we have a pretty good approximation. It's probably not exactly, but it's almost identical the whole way on this curve until you get all the way down here and then it deviates. So do we see any kind of pattern that we could further this one if you're looking at the terms? Do we see a kind of pattern at all? Do you think you could figure out what the next term would be? What do you think it would be, Abby? Factorial. Yeah. Would it be a plus or minus in front of it? Plus. So you could add another term. It would be plus x to the 9th over 9 factorial. Okay. What about this first one? It doesn't look like it follows the pattern. Okay, so x to the 1st power over 1 factorial. Well, that just simplifies. X to the 1st is x over 1 factorial is 1, so it just simplifies to x. So it does follow the pattern, but that's why it's just x, so that's good to notice. Alright, so let's answer some of these questions then after looking at this. So we said, what do you notice? Well, Eric had mentioned, and I think you guys had also noticed, with each successive term, so each time we added one, the polynomial better approximates the curve. So with each successive term, polynomial better approximates the curve. Each time we're able to find a better and better approximation. Okay. Then it goes on to say what is y1 of 0, what's y2 of 0, what is y1 of 0.2, and what is y2 of 0.2. So before we get started, the first one from up above, when we just had y equals x, this was considered a first degree Taylor polynomial. What do you think this one's considered? Something degree Taylor polynomial. What degree do you think it is? Abby? Seventh, yeah. It's a 7th degree Taylor polynomial. Okay, so let's go on to answer the questions then. So y1 of 0. Well, y1 is what? What's our y1 function? Think about what we plugged in the calculator. We had y1 and y2. What was the y1? What function did we plug into our y1 key in the calculator? Yeah, sine. So we're asking what is sine of 0. And sine of 0 is what? 0. Okay? Then it wants to know our second function, so y2, what is it when you plug in 0? Well, that would be plugging 0 into this. So we would have 0 minus 0 cubed over 3 factorial plus 0 to the 5th over 5 factorial minus 0 to the 7th over 7 factorial. So our answer is what? What's 0 plus or minus a bunch of zeros? 0. Okay? So our approximation, y1 is our original one, the y2 is our approximation. At the center, they're starting at the same spot, the centers are the same, so the approximation of the center is the same. But now they want us to find the approximation at point 2. So y1 of point 2, well, y1 was sine, so sine of point 2. And I think we actually have that from up above if you want to reuse the information. It was 0.199. y2 of 0.2. Now we have to plug this into this Taylor polynomial we have. 0.2 minus 0.2 to the 3rd over 3 factorial plus 0.2 to the 5th over 5 factorial minus 0.2 to the 7th over 7 factorial. And I want to get an answer for this. So you have it in your y2 keys. If you want to use the table feature on your calculator, you could go in and find the value of 0.2, or if you want to actually just type this in and hit enter. But find the value of y2 at 0.2. So either use the table feature and figure it out, or type it in. And let's get your approximation to 3 decimal places. Anybody get it yet? What'd you get, Madison?
0.199.
Yeah, 0.199 is your approximation. Is the approximation pretty close to y1? Yeah, so we've used this curve. Remember, this approximates a little better than our original first degree Taylor polynomial. The approximation was close with the line from up above, but there was some error with it. But we used the 7th degree polynomial, we were able to get a much closer approximation. Now I'm sure if you go out many more decimal places, you would find discrepancies somewhere, but up to 3 decimal places, it's very close. So really used to approximate some other functions that are hard to get an actual value for. We ready to flip? Anybody still copying? Alright, go ahead over. Got some people here with some interesting hair and headdresses. Alright, so the definition of an nth degree Taylor polynomial. So we are going to talk about this. It's up to you. Would you guys like a note card to write any of this information down? We're going to talk about these definitions. I have them up here if you want them. If you want to do it tomorrow and just pay attention today, you could write the note card tomorrow. So we have Taylor here. So Taylor created this polynomial, and he's going to represent this polynomial. It's always the Pn of x. Okay, where n is that degree that we're talking about. So it has a center at x equals c. This is your center of approximation. For the sine function, our center of approximation was at that 0, 0, so at x equals 0. And the Taylor polynomial then, f of c. This is your original function. So your original function. Plus f prime of c times x minus c. Well, this f prime of c here, technically, if to follow the pattern, that's over 1 factorial, but 1 factorial is just 1. So this is your first derivative, which you know f prime of c, so first derivative. It's going to continue on. This would be your second derivative. All the way until wherever this finishes, whatever nth degree polynomial you're doing, so this would be your nth factorial, or sorry, nth derivative. So this form at the end here, this is something when we're talking about Taylor polynomials that's going to be really important. So I would probably recommend if you memorize this for the Taylor polynomials, because this is how the function is set up. The polynomial is set up with this, but the first few terms, like n factorial of 1, that goes away, so that's why they're not represented at the beginning. So that's going to be important to know for the Taylor polynomials. Okay, it's called an nth degree Taylor polynomial for f centered at c, and that's named after Brooke Taylor, the English mathematician there. Alright, so a first degree Taylor polynomial is a tangent line to f at c. So we dealt with that in the first example. The example of that, we had a y equals x. Well, that's a line, and it was the tangent line at that point at 0. It was the tangent line at 0 there. So that was the first degree polynomial. Note 2, so this here is the coefficient of the x minus c to the n term. So if you look, what they're referring to is this part up here that I had you memorize. This whole first part is a coefficient. So that will actually be some value. If c is equal to 0, then the Taylor polynomial function, evaluated at 0 there, this is what's called an nth degree Maclaurin polynomial for f. So this guy here is Maclaurin. He actually came up with this first. So he came up with this polynomial being centered at 0. So that's what we dealt with in the example with sine. It was centered at 0. So he actually came up with this example first, and then Taylor created the rest of the series and expanded upon that if your center was moved somewhere other than 0. So that's why up here for Taylor it says x equals c, the center of approximation, because Taylor found the way that we could change the center of approximation. Where with Maclaurin was like the example we did on the previous page. They told us it was at the center was at 0, or we know that the sine function started at 0. So that's what's known as a Maclaurin series, okay? So if they're talking about this guy here, or they explicitly say in the problem, it's a Maclaurin polynomial, you already know, if they don't tell you, the center is at 0. So if you want to write that down, you know the center will always be 0 here. It's the Taylor polynomials up above where the center of approximation could change. Alright, and I think we may have time to look at this example 3. So we're going to go ahead and start example 3. Find the Maclaurin polynomial of degree n equals 5 for f of x equals sine x. Then use the Taylor polynomial of degree 5 to approximate the value of sine of 0.1 using correct notation. Find the error for your approximation and determine an interval in which sine of 0.1 could actually live. Finally, compare your approximation to the actual value of sine of 0.1. Is it in your interval? Okay. So the first thing, they're talking about a Maclaurin polynomial. So we know the center is where? 0. And we're dealing with the sine function just like we were on the previous page. So we know that the sine function starts at 0 there. So the original, and they're talking about n equals 5. So how many derivatives do you think we're going to have to take? If we're talking about a 5th degree Taylor polynomial, we're probably going to have to take how many derivatives? 5. We're going to have to find the 5th derivative. So first, f of x equals sine x, okay? F prime of x. We have the first term, first derivative, second derivative, all the way up to the nth derivative. Well, they're telling us n equals 5, so we need the 5th derivative.
Okay, so the fifth, and the degree isn't the same as the nth term.
Correct, because your original one, see, this would be your, the n is representing your derivatives. Yes. Alright, so f prime of x would be cosine of x. Second derivative, negative sine x. Third derivative would be negative cosine x. Fourth derivative, sine x. Fifth derivative, cosine x. Okay. Now instead of rewriting all of these, I'm just going to use what I already have there so I don't have to write two things. But if I evaluate all of these at the center, we need to get our values for these. So sine of 0, well, we said that from before was 0. Cosine of x was 1. So now we can use those two to fill out the rest of our derivatives. Well, that one has to be 0, negative 1, 0, and 1. Again, that's all of them evaluated at 0. So now let's use the Taylor polynomial and see what kind of approximation we can get. So we're going to use these here to plug into the Taylor polynomial, or in this case, since it is centered at 0, it will be the Maclaurin polynomial. We're going to plug it in. It's going to reduce to what we can use for our approximation. So sine of x is approximately, well, the original is 0. That's the original term. Plus the second term, well, we had 1, and it's over 1 factorial x to the first. So that's going from this spot here. The first derivative evaluated at 0. It's technically over 1 factorial, so I wrote it, but 1 factorial is 1, and x to the first power, so that's where that came from. Now we're going to move on to the second derivative part. So plus second derivative was 0 over 2 factorial x squared. And we're going to get, it is negative 1 for the third. So plus negative 1 over 3 factorial x cubed. I'm going to run out of room, so I'm just going to write it below. The fourth one is plus, we get 0 again over 4 factorial x to the fourth. And for the fifth derivative, we get plus 1 over 5 factorial x to the fifth. Again, and they told us to use a polynomial of degree 5, so up to the 5th derivative, so we're using up to the 5th derivative here. Now, this will simplify a little bit. We're going to have a few terms that go away, right? I mean, we have 0 here times anything is 0. 0 here times anything is 0. This is a 0 to begin with. So we have this first term. That really just simplifies to x. Then we have minus x cubed over 3 factorial. That term stayed. And plus x to the 5th over 5 factorial. So for sine of x, this is our approximation of the 5th degree. Do you see a pattern where if they ask for a higher degree, you could create more terms? Kind of like we talked about on the first page. Do you think you could figure out what the next term would be if we were asking for it? I bet Abby can. Yeah, sure, go ahead.
X to the 7 over 7
Yeah, and it would be minus, exactly. So if they ask for a higher one, we see the pattern here for sine x, so yes, you could find it. But they only wanted us to use the approximation up to the 5th degree. Okay. So actually, before we even do it, this method, mathematically, is actually how your calculator is programmed to find these values of sine. So you have this, but you would have the minus 7x to the 7th over 7 factorial. You just keep expanding that formula further and further. You're going to get a better and better approximation, just like we found on the front page. The more terms you add, the better approximation. So your calculator uses one of these approximations that's used a lot further, and that's how it actually finds the value of sine in your calculator. So now we need to find the values of sine at point 1. So sine of 0.1, and we're going to say it's approximate, so your squiggly lines, approximate, and we're going to use the approximation from up above. So 0.1, 0.1 cubed, not 0.3 cubed, 0.1 cubed, over 3 factorial, plus 0.1 to the 5th over 5 factorial. Go ahead, plug that into your calculator and get the approximation. And we can take this out pretty far. We need to go to 1, 2, 3, 4, 5, 6, 7, 8, 9. Go to like 10 decimal places if your calculator will go that far. Did we get a big long value yet? Up to 10 terms? Alright. What'd you get?
0.099833467.
Okay. 0.099833467. That is what I got. So that's your approximation using the Maclaurin polynomial there. Or in other words, it's the Taylor polynomial but centered at 0. So that's, again, the special case, the Maclaurin polynomial. So they asked us for one more thing. They said to find the error of that. So we can figure out what the next term would be. I think Abby already told us the next term was going to be minus x to the 7th over 7 factorial. So we want to find our max error. Maximum error. Because we want to find the bounds within, or the bounds that our answer would be within, or our approximation would be within. So we want to find the max error, so R for like the remainder or the error, of 7, because 7 is the next term. We stopped at n equals 5, but we need to find the error for the next term. And again, the next term would have been negative x to the 7th over 7 factorial, exactly what Abby had told us. We can find the value of just that term. So again, at point 1, find the value. So plug point 1 into that. And what is the value of just the 7th term at point 1? So evaluate this, and you should get a big long decimal also. Your calculator may put it in scientific notation, depending on the calculator. Did your calculators do scientific notation? Alright, so I got 1.984 times 10 to the negative 11th. Pretty close to what you got. You got negative? Well, yeah, so the negative out front, yes, it should be negative. So you get negative 1.98 times 10 to the negative 11th. So in other words, if we write that all out, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 198. So that is the value of the 7th term. 10 zeros there and then 198. So the error for the next term, we know it has to be from this value that we just calculated. And we need to, well, the 7th term is being subtracted. It's a negative. So we need to subtract it from this value, and that will give us the bounds within where our approximation should be at point 1. So I'm going to erase this up here so I have some room. So I'm still referring to this number. So for my max error, I get this, this, and this, so my conclusion would be so sine of point 1, and that's that sign that kind of looks like an E, that means like within. You draw a C and then put like a line in the middle. That just means within. So we have our approximation here of the 5th degree. We need to take our 5th degree approximation and subtract off the 7th term, because we know the 7th term was going to be minusing. So go ahead and take this term, your approximation. That's our upper bound. We know at most it's going to be that from the 5th degree, but we know it has to be within that and whatever the 7th term is. So when you subtract those two, you would get your lower and upper bounds. All right. We'll pick up there tomorrow, but those give you your upper and lower bounds. Class ended.